All right, so let me very briefly review what we did last time.
Please, may you
So,
give the permission for recording?
oh yeah, in just a second. Uh-huh. All right, so last time we discussed how to define what I call the weak n category object in a model category, or more precisely, the base model category, capital V. For example, V could be sets, in which case you get n categories, or it could be simplicial sets, in which case you get infinity n categories. And the model structure we discussed in great detail. It will be functors from a model structure on. So the category here is constructed inductively. So you construct it for all n by induction. And on each step, if n equals 0, you simply take capital V. And if n is greater than 0, you take the model category of globular complete single objects valued in the previous step of the induction, what you constructed as a previous step. So this mirrors very closely our intuition that, so basically this statement, what is expressing is that, let me pick some color. And infinity n category is a category homotopy coherently enriched in infinity n minus 1 categories. Meaning you have objects, and between any pair of objects, you have an infinity n minus 1 category of morphisms. And this construction formally expresses this idea, so it's has in principle a wider range of applications, and you can initially imagine. And some more examples will include chain complexes, which will give you something called a differential graded n category. And examples of interest to us will also be various categories of simplicial pre-sheaves on various sites. And I already mentioned that we will be interested in the Cartesian site, which, as we will see later, will be encoding smooth families of objects and morphisms. And the idea behind this is that, for example, an infinity zero category is not just a simplicial set or infinity groupoid anymore, but a sheaf of infinity groupoids. And in fact, we'll make things a bit more complicated by adding another copy of Cartesian spaces that encodes isotropies. But this will be discussed a bit later, maybe not to overwhelm you immediately with all those details. And of course, there's also a symmetric monoidal structure present, which is encoded by gamma. So that will give us what is called a smooth symmetric monoidal infinity n category. Okay. All right, so today maybe I'll start with an example of such a construction without smooth families. So we are going to construct bordisms as a higher category, more precisely as a symmetric monoidal infinity D category.
Please may you remind what gamma space is encoding there.
The gamma here is encoded in the symmetric monoidal structure. And each of the copies of delta is encoding a categorical direction, categorical composition, if you want, of K morphisms, where K ranges from 1 to D. Okay, so let's see how this works.
In the language of field theories, it is encodes the map between various field theories. Yes.
Right now, we don't have a field theory yet. In fact, we will define one. So in fact, you can see a definition right here at the bottom. So a functorial field theory will be defined as a morphism from the bordism category that we just constructed to some category of values, or some smooth, or in our case, just symmetric monoidal infinity D category of values. And I also wrote the words derived here to indicate that in our case, all objects are cofibrant, but you may need to phymetrically replace V in order to get the correct motion. But at the moment, we are just defining the bordism category, not a functorial field theory yet. So the construction present on this page will be, of course, very familiar to you. We have seen it in several incarnations already. So let me just maybe briefly review what happened previously. And so in general, we assigned to every object. So in our case, this will be an object L in gamma. So basically a finite set or a finite pointed set, and a D tuple of simplices M1 to MD. We assign to it a category of which we will take the nerve. This will be our simplicial set. So what kind of category do we assign? Well, morally, objects in this category will be bordisms cut into a grid. You can see a picture on the right for the case when M has two simplices, one 3 simplex and one 2 simplex. And what it means, you in your bordism grid, you have three morphisms in the horizontal direction and 2 morphisms in the vertical direction. So 3 columns and 2 rows. And of course, higher dimensional pictures are also possible, but much more difficult to draw. So the first Geiger you have to specify is a d-dimensional smooth manifold M, which will be the bordism. More precisely, it will be a bordism together with this color, a small open neighborhood of the bordism proper. Next, according to what we previously learned about gamma spaces, and now let me actually scroll back to show you what oh yeah, right here. So as you may recall, the to encode the operation of disjoint union as a symmetric monoidal structure, we use this map capital P. So capital P is a map from your Bordism, like the picture on the left, to a finite set, or if you prefer, pointed finite set. Doesn't really make much difference. And the pre-image over every point of this finite set will be a bunch of connected components in the Bordism, like a bunch of components here, a bunch of components here. Here you have just one. And the pre-image of the base point, if it's present, is a trash. It's called a trash bin. It's ignored. And so the idea here is that when you want to take the disjoint union of some elements in this tuple, for example, the first two elements in the tuple, you want to take their disjoint union. What you will do is you will take this map capital P and compose it with a map of finite sets that sends the elements 1 and 2 to the same element. And the effect of this will be that the pre-image of the element 1 in the codomain will be the union of these two components. And do notice that the operation of union, thus defined, is strictly, well, it's the relevant identities are satisfied strictly and not up to an isomorphism or some higher coherence. Since if you just say like, oh, just get the disjoint union of these two guys, well, which one? And if you're, it's difficult to make it strictly associative, for example. But in this approach, everything it will be strict from essentially by definition, because composition of maps of sets is strict. Okay, so that's the meaning of P is basically unchanged. And next, we also have the what I call a cut grid on M. So previously, we explained how to encode composition in a single direction using cuts. For example, here you can see 1, 2, 3, 4 cuts in the that allow you to compose in the horizontal direction. And for a cut M grid, you have a cut tuple for every direction. So you have D directions in which you can compose, and for each of those directions, you have a corresponding cut tuple indexed by the corresponding simplex. So for example, in this picture, you would have a cut 3 tuple, so that's the vertical cuts, 4 vertical cuts, and a cut 2 tuple, that's the 3 horizontal cuts. And in addition to imposing the definition of a cut tuple that we previously studied, which was given somewhere before gamma spaces, I guess. Yes, right here. And the picture we gave was that you have a bunch of cuts. Each cut knows what part of Bordism is before and what part of Bordism is after. So that's what we're denoted by M less than 0, M greater than 0, and the cut itself will be M equals 0. And this is suggestive of the existence of a cut function H, so that the pre-image, so H will be a function from M to real numbers, smooth, such that 0 is a regular value, and the pre-images of the negative ray, 0, and the positive ray are precisely the 3 indicated subsets. So a cut tuple would then contain several such cuts in succession, and the corresponding sets will include into one another. So all of this information is still present here, and now is present in every direction in which we want to compose. And furthermore, you have a transversality condition, which is a new. The transversality condition says, so previously notice we were able to define a cut function for every single cut. And the transversality condition says, if you pick several cuts in several directions, so for example, you can pick a cut in one direction like this, and another cut in a vertical direction like this, then each of those two cuts has a, let's call them m and n, so this will be n greater than 0 and less than 0, and here you have m less than 0 and m greater than 0. Now, for each of those two cuts, you have a hike function inducing these positive and negative regions. And the transversality condition says if you pick several cuts in different directions, it is possible to construct a single, what I would call multi-hike function, or you can think maybe of a better name. It will be a function from m to tuples of real numbers, as many real numbers as you have as the number of directions you have chosen to work with. And the idea behind this cut function is that projecting this multi-hike function to individual directions produces a hike function for the corresponding cut. Now you may ask, how is it not possible that why not simply take the hike functions, one for each cut, and simply assemble them in a sort of tautological multi-hike function? But this is where the sort of the transversality condition comes in. It says regular values of h must form an open neighborhood of 0. And the sort of picture you should have in mind is something depicted on the right side. So this is a case when S has two elements. And your multi-hike function will map M to R2, which is a coordinate plane. And the pre-images of various regions in this plane will be giving you the corresponding regions for M and N. So for example, if I took the positive half plane, say the region where y is greater than 0, its pre-image will give me m greater than 0. And if I take the, say, the left half plane where x is less than 0, its pre-image will give me n less than 0. So it may be instructive to just draw a picture where the transversality condition is violated. And here is one example. I mean, as you can guess, it will be something non-transversal. So imagine this is a cut in one direction, and this is a cut in another direction, and here they are tangent. then it is not possible to construct such a multi-height function. For example, because you see a necessary condition for the existence of such a multi-height function in the case of true cuts on a two-dimensional boardism is that the changing vectors to the boardism at the intersection point, the changing vectors to cuts are linearly independent. So here is one tangent vector, and here is another tangent vector. But if you look at this picture, the tangent vectors will be pointing in the same direction, or maybe opposite directions, and they will not be linearly independent. They will be proportionate. So in this case, the transversality condition is violated. So that's a non-example. So that's it. Basically, there's one more condition which already resembles something we have seen previously. That's the compactness condition. If you recall previously, the compactness condition said if you take the core of your boardism, which is everything located between the leftmost cut and the rightmost cut, and formally you just take the intersection of so the core in this case would be let me try to match this color. I hope I can do it. So here the core is the intersection of, say, m at least 0, and in this case it will be m at most 3. And it's this core part, so after we discard colors, that this part must be compact. So for higher categorical situations, the core is defined in a very similar way, only now you take basically what was previously the core in each direction, and you intersect them all. So for instance, in this picture, it would be the area inside all cells, but not taking any of the colors. And it is this region that has to be a compact topological space. Any questions so far?
Please may I comment a bit more about globularity condition.
Say again, comment a bit more about what?
Globularity condition.
Oh, we haven't started that yet, so that will be the next topic. Globularity is next.
Thank you.
Any questions about compactness, transversality, or the definition in general?
What is the intuition behind transversality in our case?
Well, it's simply that it's kind of like meant to somewhat resemble what you previously may have known as a manifold with corners. In one of the definitions of a manifold with corners, you would also have a similar, like what exactly is a manifold with corners? Maybe something like a picture like this one. I don't know, like. And these corners here the tangent vectors will be in this direction and this direction will be linearly independent. So in principle, I would say the transversality condition was inspired by this notion of a manifold with corners. I mean, it's basically what you get when you cut up a bordism in the other direction. Where exactly is it used later? That's a great question, actually.
For considering some vectors and fields, possibly. Yeah.
Sorry, say again?
For observing some fields and vector fields, possibly. This condition is needed for this.
Which vector fields, maybe I should ask, because we haven't defined any vector fields yet.
Possibly it is maybe used. I just suggest.
Oh, well, we'll see maybe more explicit examples a bit later, but let's see what if I can give you something simple. Well, I guess it's used when you start cutting out hangles. You want them to be cut out transversely, and a hangle is a bordism of a specified shape. So when you prove the geometrical bordism hypothesis, the hangles will be bordisms of a pre-specified shape. And if you allow non-transversal intersections, in principle, you may gain some strange bordisms that you didn't want to have, that may not be necessarily classifiable even in terms of the GCH. It may not make a Hango decomposition. So yeah, so the use of this transversality condition is basically buried somewhere deep inside the proof of the GCH. I'm pretty sure it's not used anywhere in the proof of locality, but at least I can't recall any use of it in locality. So, but probably it's we should point it out explicitly where it's used in the proof of GCH. Yeah. All right. So let me now comment a bit on globularity. And globularity makes your picture of a bordism, which we previously drew like this, or like that, this grid here. What globularity does for you, if you may recall, globularity forces the vertical morphisms to be invertible. And the easiest way to force something to be invertible is to force it to be identity. That's exactly what we are going to do. So we are going to take this square bordism and we'll force the vertical bordisms here to be identities. So the two vertical directions are collapsed to a point. And what remains is a globular bordism. So where you have a, if you take the source, for example, in the first direction, so this will be this just this green line. You discard the blue lines, and that's just a point.
As I understand, with green lines collapsed into points, yes? There, on this picture.
No, we already collapsed this line into this point here. The remaining lines are colors and they are still present. So the colors are still present because, well, let me actually draw the color for you. So there is still a two-dimensional color surrounding the bordism. but the core of the vertical bordism was collapsed to a point. And formally speaking, this you would express this by saying that extracting a vertex in the i's direction. So, for example, in the first direction, extracting a vertex would amount to extracting this vertical segment here. And this must give you a simplicially degenerate bordism in the directions after I. So in our case, that means this resulting bordism, which is a one-dimensional bordism in the vertical direction, must be vertically degenerate. And being vertically degenerate means that these two horizontal lines must coincide. And that's exactly what happens here. So in a neighborhood of this point, the horizontal lines coincide. So you can still work just fine with such bordisms. You can glue them easily and everything works as before. It's just that they are now globular. And such bordisms are perfectly sufficient to cut or present any bordism as a composition of bordisms of this form. Assuming the original bordism is itself globular. Okay, so that's the
This
that's the
condition is needed, as I understand, for constructing some invertible field theories, yes?
not necessarily all of them, because the reason we introduced globularity in the first place is we really don't want to have two different notions of non-invertible one-bordisms. Because in this picture, you see you have, in principle, two distinct types of one-bordisms. One is vertical and the other one is horizontal. Like in this picture, a horizontal one-bordism and a vertical one-bordism. This will create problems, for example, for the geometric bordism hypothesis, because having two different notions of non-invertible one-bordisms allows you to have two different notions of dualizability for objects. You can either be dualizable in the horizontal direction, or you can be dualizable in the vertical direction. And basically, this implies that at least I'm not aware of any way to formulate GCH with such different types of dualizability. GCH only talks about a single type of dualizability for objects, for morphisms, for true morphisms, and so on. So to avoid having different types of dualizability, we must avoid different types of non-invertible one morphisms. And to avoid this, we force the vertical bordisms to be identities. This precisely achieves this goal that we initially posed. All right, let's move on to maybe I should point out that there are still some bits left. All of those bits, like some refinements, which will be smoothness, isotropies, and geometric structures, all of which are intimately connected to this category here, the enriching category. And that's what I'm going to talk about next. smooth category theory and maybe a bit of at least one example of how smooth category theory is maybe a bit different from ordinary category theory. All right, if there are no more questions left, then we should move on. Keep this one on the left side. All right, so smooth category theory basically studies, instead of categories as your basic objects, you have sheaves of categories on some site. And more generally, you want to talk about, instead of functors being usual functors of ordinary categories, you would have morphisms of sheaves of categories. And instead of natural transformations, you would have basically sheaves or natural transformations between two such morphisms. So let's recall that we previously talked a lot about the Czech model structure. We talked about the Czech model structure and simplicial pre-sheaves. More specifically, simplicial pre-sheaves on the Cartesian side. And these were this was defined as the left Bowes-Wilk localization at Czech nerves of the projective or injective model structure at Czech nerves of covering families. And much more generally, we can also define the Czech model structure on pre-sheaves valued in any combinatorial model category V. It's basically defined in exactly the same manner. It will be a left, I guess I should say left proper, because that's a necessary condition for left Bowes-Wilk localizations. But that's not a restrictive condition, because any combinatorial model category is clearly equivalent to a left proper combinatorial model category. So you would start with you would start with the category of pre-sheaves on Cartesian spaces valued in V. And you will construct a set of morphisms S given by taking the Czech nerve of arbitrary covering families and transiting it with an arbitrary object A of the enriching category V. And transiting here, just to remind you, transiting is a functor. In this case, it will be a functor. Well, first of all, this is a morphism of pre-sheaves here. So the operation of transiting will be applied individually to the values of these pre-sheaves. So really, I only have to define for you how to transfer an object of V and a set. This operation sends A, comma, say, let's go T to the coproduct of T many copies of A. And when you perform such a Bowes-Wilk localization, the local objects will be pre-sheaves that satisfy the infinity descent condition. The infinity descent condition is stated in exactly the same way as before. The restriction map from the value of your pre-sheaf F at any object X of your site, you have a restriction map to the right side. The right side is known as compatible families or homotopy coherent compatible families. And is formally speaking, is just a homotopy limit over the diagram indexing the check nerve. Then you take the corresponding intersection of opens and you evaluate f of this intersection. So everything is exactly the same as for simplicial sets.
Dmitri, can you hear me?
Yes?
So one quick question. So concerning the definition of derived functorial field theories. So when we derive, we do so over the infinity one category of infinity n, symmetric monoidal infinity n categories, right?
That's
Because
right,
we only
yes.
present it as a model category. So
Yeah.
why is it enough to have this deriving over an infinity one category of infinity n category? Shouldn't there be a higher dimensional version of a model category so that we derive over this and get a...
One answer would be here is that deriving means replacing objects with weakly equivalent objects, and which presumably have better properties when you map in or out of them. And weak equivalence in the infinity categorical setting, that's an invertible morphism. That's something that is already present in the infinity zero category even. Of course, you could theoretically consider higher non-invertible morphisms, but such higher non-invertible morphisms will never be useful for deriving anything because we don't really derive using morphisms other than weak equivalences. And you're not going to see any new weak equivalences when you consider higher non-invertible morphisms. So the underlying, if you want, in the infinity D category, infinity D plus one category of infinity D categories, the invertible morphisms are exactly the same as in the infinity one category of infinity D categories. There is no difference. You don't get any new invertible morphisms. So even though we could construct an infinity D plus one category of infinity D categories, in fact, that's not very difficult and quite doable in our setup. But it's just not going to give you anything new. It will be exactly the same story as before.
That makes sense. Thank you.
Right, more questions? All right, let me move on to maybe some of the simplest possible examples of smooth categories. So here, capital V will be just the model category of categories equipped with its canonical, also known as natural or categorical model structure. In this model structure, weak equivalences are precisely equivalences of categories, such as, say, fully faithful and essential surjective functors. And let's try to give you a simple example as possible. And I chose vector spaces as an example. So we want to construct something like a smooth category of vector spaces. Well, that's in principle not so difficult. To specify a smooth category, you have to specify a contravariant functor from Cartesian spaces to categories. Meaning, for every Cartesian space S, you have to specify a category. In our case, this category should be morally at least. You can, for example, imagine something like so here is maybe S. Here's a picture of S. And you want a smooth family of vector spaces indexed by S. And that means over every point of S, you have a vector space. And these vector spaces must somehow depend smoothly on the point. And you immediately have multiple choices for your. You can now see is like basically have different choices depending on your preferences. So as one alternative, maybe I should have mentioned it before, but so as one alternative, you can take the category of vector bundles over S. And in principle, that's a legitimate choice. It is a bit too restrictive for our purposes because you will see in a second, we will want to quickly move to infinite dimensional vector spaces. And because, for example, quantization tends to produce infinite dimensional vector spaces. And the notion of a vector bundle with infinite dimensional fibers, well, there are several competing notions, and it's in general difficult to single out the most preferred one. Another alternative to taking vector bundles for somebody who is familiar with algebraic geometry, you can maybe say, oh, let's just send S to the category of modules over the algebra or ring of smooth functions on S. And we know from algebraic geometry there is something called the Serre-Swan. So you should be thinking of the Serre-Swan theorem here. And just to remind you, for smooth manifolds, the Serre-Swan theorem says the category of vector bundles over S is equivalent by Serre-Swan to the category of finitely generated projective modules over C infinity S. Another name for finitely generated and projective is dualizable module. Dualizable in the sense of monoidal categories with respect to the tensor product as a monoidal structure. So here what we did, we dropped the finitely generated condition and the projective condition. So the finitely generated means more or less fibers are finite dimensional, and projective means sort of you have some sort of local triviality condition. So if we drop both, we get the category of C infinity S modules. Now, the problem with this new definition is that we also remember to specify a smooth category, we have to specify for every smooth map of Cartesian spaces, we have to specify a pullback functor that will take a C-indexed family of vector spaces and produce an S-indexed family of vector spaces. And for vector bundles, that was quite trivial. Pullback of vector bundles is defined as a fiber product. Or in algebraic terms, you will simply change the tensor product. as indicated here on the right side. But this transfer product, if we want to do something infinite dimensional, it will be poorly behaved in the infinite dimensional cases. The one reason for this is that for infinite dimensional vector spaces, you typically want some property analogous to completeness, because you want to do maybe a bit of analysis or stuff like the spectral theorem, for example, requires completeness. To talk about eigenspaces and prove theorems about eigenspaces, you need completeness. And this is just this operation, this type of transfer product, it's not going to be complete in general. So you perhaps want to replace this with some completed transfer product, and of course the question is which one? In the traditional setting of functional analysis, there are so many different transfer products, the projective transfer product, the injective transfer product, and a few more. They all have different properties. It's unclear which one will be beneficial. So let me maybe provide a different answer that doesn't require you to use any functional analysis. And it's what I call smooth vector spaces. So what exactly is a smooth vector space? Well, the category of smooth vector spaces will contain the category of ordinary vector spaces as a full subcategory, but we'll have many more objects. So formally speaking, let's consider the category curly A of what I call smooth abelian groups. Which is formally defined as a category of sheaves of abelian groups on the side of Cartesian spaces. Or, if you prefer, there is an equivalent definition which says it's a category of abelian group objects in the category of sheaves of sets. This may seem like almost a tautology, but in principle, it does reflect certain fundamental differences in philosophy, and the answer on the right side is the Topos theory answer, and the answer on the left side is maybe more of a traditional algebraic geometry answer, maybe. And of course, Topos theory tends to be more correct, but in this case, it's exactly the same. Next, we can look at the category of, so this category A is equipped with a transfer product over integers, which is given by taking the object-wise transfer product over every object in your site, and then sheafifying the resulting pre-sheaf. And with respect to this transfer product, you can form the category of commutative monoids. So that's what I would call smooth commutative rings. And if you have a commutative monoid object, you can talk about modules over this commutative monoid object. So you can talk about modules over smooth real numbers. And that's what we call a smooth vector space. It's a module in the categorical sense over the commutative monoid of smooth real numbers. And probably I should have defined, I guess I forgot to define smooth real numbers. So the value of this sheaf on some Cartesian space S is simply the commutative ring of smooth functions on S, which expresses the idea that a smooth family of real numbers indexed by a smooth manifold S is simply a smooth function from S to real numbers. Okay, and I also mentioned we want to have eventually some type of completeness condition. And of course, completeness always goes together with Hausdorff type conditions, or in the language of algebraic geometry, we would say separated. So completeness guarantees existence of limits that we want to exist, like existence of integrals, existence of derivatives, and separatedness guarantees uniqueness of limits, in particular, uniqueness of derivatives, uniqueness of integrals, and other things we want to do in our space. So completeness and separatedness go together. And as it turns out, in this case, there is a very elegant way to formulate completeness and separatedness. So the category of modules over any commutative monoid object, it naturally has a monoidal structure given by the tensor product over this commutative monoid. And in particular, you can talk about duality. So the dual, let me say maybe the dual of a vector space V is defined as the internal harm from V to the base field. And now, in a purely abstract manner, you can construct a canonical map from V to its double dual.
Dmitri?
Yeah.
Could you say again what mod RC infinity is?
Yeah, mod RC infinity. So in any if you have a monoidal category like sheaves of abelian groups, it has a symmetric monoidal structure. In any symmetric monoidal category, you can talk about commutative monoids, and you can talk about modules over commutative monoids. These are all defined in abstract categorical fashion. Let's see, let me just very briefly. So for example, what is a commutative monoid? A commutative monoid in our case will be, let's say, M is not taken, right? So M, a monoid will be an object in A together with maps like a multiplication map. And the unique map, what is the unique of this monoidal structure is the integers. And these maps, these morphisms, have to satisfy, for example, conditions like associativity, which can only be expressed purely categorically. And you can multiply these two factors using mu, or these two factors using mu. And then you can multiply the remaining two factors, and this diagram has to commute. And likewise, you can write down a completely analogous definition for modules. So X, a module over A, so modules over M, sorry. So this will be X, some object in A, together with a multiplication map And this multiplication map has to satisfy the usual axioms. But maybe I should also say much more concretely, and in fact, I did try to say it here. So what this definition of a smooth vector space boils down to concretely is that, should probably explain here. So a smooth vector space V is given by specifying for every S a Cartesian space, you have to specify Vs, which, looking at this definition, will be a module in the ordinary sense, in the sense of abstract algebra, over smooth functions on S. And furthermore, you have restriction maps. If you have a map F from S to T, a morphism in Cartesian spaces, you have a restriction map or pullback map that goes from Vt to Vs. And this map is linear, and in fact is compatible with the actions C infinity T, sorry, C infinity S. So there's an action of C infinity S on Vs. And there's also an action of C infinity S on Vt because the map F induces a homomorphism of algebras from C infinity T to C infinity S. One moment, did I screw up somewhere? Let me see. Yeah, I guess I should say C infinity T in both cases. That will be more. Yeah, so the restriction of scalars from C infinity S to C infinity T provides an action of C infinity T on the right side. But morally, you should simply think of, let's pick a different color for our morality. So morally, you think of Vs as smooth maps from S to V, where, as you know, maps from a set or space to a vector space, they have themselves have a structure of a vector space, and in fact, a module over the ring of functions on S. And as usual, the Unega lemma, once you have the definition, the Unega lemma turns morally true statements into factually true statements. This sounds like a concept from philosophy whose name we should know, but I don't. So if there are any philosophers here, perhaps you could tell us, but what we call something that turns morally true statements into factually true statements. All right. So that's how you think about smooth vector spaces. Do I want to see maybe some examples? Let me give you at least one example before I talk about smooth limits and smooth colimits. Let me give you one example. In fact, I can give you two examples. Let's fix some Z smooth manifold. We can consider the ring or the vector space of smooth functions on Z. The ordinary construction just gives you an ordinary real vector space. But in fact, we can construct this object as a smooth vector space. How does it work? Well, it's incredibly easy. You pick a Cartesian space S, and you have to specify what it means. What does it mean to have a smooth map from S into this vector space? Or in other words, what does it mean to have a smooth family indexed by S, a smooth family of smooth functions on capital Z? And after thinking for a few seconds, you probably should come up with this answer. It's just smooth functions on S times Z. And the pullback maps work in the obvious way if we have a map from S to T. Of course, it induces a pullback map from smooth functions on T times Z to R to smooth functions on S times Z to R. By precomposition with this map applied to the first component. So maybe at this point we should emphasize, as I did many times before, of course, but imagine doing the same example in the traditional setting of functional analysis and topological vector spaces specifically. To define this vector space as a topological vector space, you would have to introduce, well, the correct topology here is called the Whitney topology. And it's actually not so easy to introduce it and prove it is a topology. And the Whitney topology is basically defined as the core limit taking over all compact subsets of capital Z. And then for every such a compact subset K of Z, you would define a topology on smooth functions on K valued in R. And this topology will be the limit topology taking over all functions differentiable K times. And on functions differentiable K times, where K is any non-negative integer, you will introduce a topology which will be basically the Banach space topology induced by taking all partial derivatives of order K of your function. So it's actually quite a construction, not so easy to define and difficult to prove properties. And here I basically got it for free. This is actually, that's the entire definition. And let me give you maybe one more example, which will be intimately connected to this one. I mentioned the internal home, in particular the dual vector space. So we can take the internal home from C infinity. Perhaps I should underline this just to remind you it's not just the usual vector space, but a smooth vector space. And I take internal home from this to the ring of smooth real numbers. So that's what we also call the dualization, the dual of smooth, getting thick. If you are familiar with a bit of functional analysis, you may already guess what the answer should be. So that's what we would call the compactly supported distributions on Z. let me offer some very brief justification why it should be the case. Well, let's unfold this definition of the internal form. What does it mean to specify a morphism from this smooth vector space to real numbers? Well, it means that for every S, I have to specify a linear map from smooth functions on S times Z to R to smooth functions on S. And this linear map must be compatible with pullbacks with respect to S. So in particular, taking S to be a point, I get a smooth map from smooth functions to real numbers. And furthermore, since the map for arbitrary S is compatible with pullbacks, I see that this map, let me call it psi, specifying the map psi for the case when S equals a point already uniquely determines these maps here, because the value of such a map on some element here at some point of S, well, to evaluate at some point of S, you would simply restrict to the same point here in this factor, and then apply this map psi. So this is just defined using psi on every fiber here, every point of S, so to say. But it doesn't mean that these morphisms are redundant. There is a condition in being imposed here, and the condition is that the existence of these maps amounts to saying that psi maps smooth families of functions to smooth families of numbers. Because a priori, if I just specify some arbitrary linear map, the axiom of choice allows you to construct pathological examples of linear maps psi for which this induced map is not going to land in smooth functions. It will land in some discontinuous functions. So the existence of such maps is an additional condition on psi. And the theorem I guess I have to this is probably due to well, I'm struggling to find a correct attribution, but I think this should have already been known to Laurent Schwartz, but the theorem says psi is in bijection with distributions. Psi is precisely a distribution on Z, that is to say, a continuous linear map where this space is equipped with the topology I previously mentioned to you. And again, you see how basically we managed to outcompete the usual formalism of topological vector spaces. Here we just took the dual in the purely categorical sense, and we obtained the compactly supported distributions basically for free.
Dimitri, could we use
Yep.
smooth category theory in order to have some kind of synthetic functional analysis, so to give a different foundation for the subject?
Absolutely. In fact, I have some draft in progress about this, but it's not a very long draft, but I do develop the theory of these guys, considerably the smooth vector spaces, I mean. Yeah. Yeah. So in principle, the answer is yes.
Do you know how this compares to condensed mathematics? Because people also claimed that this would be a new foundation for functional analysis.
Yeah, of course. I mean, it's in fact similar in spirit. In condensed mathematics, I think they also at some point reflexivity makes its appearance, maybe not as a central object, but at least gets mentioned. And they also use sheaves, but they use sheaves on a different site. And their site is kind of like, I would say, a bit more closely related to measure theory, because one way to formulate what their site is, its objects are compact, extremely disconnected Hausdorff topological spaces, and the morphisms are continuous maps. And the Groganic topology is very simple. It's given by finite disjoint open covers. So a partition of your space into disjoint open subsets. And it turns out, and that's quite surprising, that such a simple site with such a simple topology has a very rich theory. But that's not quite the same as our site. So in principle, the series will be a bit different, although of course very similar in the formal machinery, I guess, the categorical machinery of category series using both, but at least I find it easier to, when I talk about differential geometry and mathematical physics, I find smooth vector spaces fit more naturally, maybe. But Schulze and Clausing, they have their own sort of applications to non-Archimedean settings, where somehow, of course, the site of smooth Cartesian spaces will be useless. So there, to talk about the non-Archimedean objects correctly, I guess their setting is much, much better.
Makes sense.
All right. Yeah, and maybe as a fun fact, if we take the dual a second time, probably that's also an extension of Schwarz's theorem that the dual of compactly supported distributions, of course, as you expect, is isomorphic to smooth functions. So that's also very formal, quite formal. But there is some non-trivial argument going inside of it, but yeah, I guess I should say it's completely formal. There's something to prove here. And as a consequence, smooth functions and distributions are complete separated vector space, smooth vector spaces. Which at least shows like our definition of completeness and separatedness is at least somewhat reasonable. Okay, so there is much we could discuss about this category. For example, turns out it has a very beautiful symmetric monoidal structure, a closed symmetric monoidal structure, which is also has a really nice generalizability properties. It's what is called a star autonomous category, or also known as a rigid monoidal category. Or but that's not our focus for today. And for today, I just wanted to maybe very briefly explain smooth limits and smooth colimits, which should at least give you, I hope, some impression as to why smooth category theory is capable of bringing some analysis to the so far purely categorical setting of functorial field theory. So here is our basic setup. Let me start with the usual example of vector spaces. So you say you have an indexing set, capital I. You have what is called a diagonal functor from the category of vector spaces to the category of families of vector spaces indexed by capital I. So its objects are families of vector spaces indexed by capital I, and morphisms are just collections of linear maps. And there's a diagonal functor which sends a vector space V to a constant family where every index I, every element in the family will be capital V. Sorry. Will be capital V. And this diagonal functor has two adjoint functors, a left adjoint functor and a right adjoint functor. The left adjoint functor is known as a direct sum functor. It sends an I-index family of vector spaces because they're a direct sum, denoted using a circled plus sign. The right adjoint is known as a direct product functor. It sends an I-index family of vector spaces because they're a direct product. And it may be useful to also at least identify what the unique and co-unique maps are for these two adjunctions. So let's look at the top adjunction first. The unique map for the top adjunction, for the direct sum adjunction, will be a morphism from a family of vector spaces to the diagonal functor applied to the direct sum of this family. So in other words, here you are going to see a constant family on the right side, a constant family where every element is the direct sum of the original family. And what is this unique morphism? It will be a family of morphisms from Vi to the direct sum. And we do know such a morphism is the canonical inclusion in a direct sum. Now, what about the co-unique map? The co-unique map for some object W in vector spaces will be a map that lands in W, and its domain is the direct sum of the constant family on W. So the direct sum of a family indexed by capital I, where every element is W. So it's a direct sum of capital I, many copies of W. And the co-unique map will be a linear map from this direct sum to W. What is such a map? Is precisely the sum you you take an element here, which is a collection of elements in W indexed by capital I. Only finitely many of them are non-zero. You check their sum, and you get into W. The unique and co-unique maps for the other adjunction are completely dual. Now the unique map for some vector space W will be a morphism from W to the product of the constant family index whose elements are W. This is what is known as a diagonal map. Maps every element of W to a family where every element is W. So that's known as a diagonal. Oh, and this one is sometimes called a codiagonal. And as you can expect from this description of the unique map, the co-unique map for the other adjunction will be precisely the projections, the family of canonical projections. So that's a setting for ordinary vector spaces. Any questions so far? Okay, let me now tell you what the analog of this entire story is for smooth vector spaces. In fact, we are going to look at complete and separated smooth vector spaces. And as before, we have an adjoint triple, which I will now describe. Now, capital I used to be an ordinary set, but in smooth category theory, capital I will be a sheaf of sets on the Cartesian side, also known as a smooth set. For example, I can take capital I to be a manifold. So maybe that's the simplest possible example you should be thinking about. Capital I could be just an ordinary manifold or even a Cartesian space. Let's say even Cartesian space is even easier. And it's already interesting. Now we need to define an analog of this category, the category of I-indexed families of vector spaces. And now we need an I-indexed family of smooth, complete separated smooth vector spaces, and I is itself some Cartesian space. But that's precisely what the formalism of smooth categories is so good at. It allows us to define such families. And I guess I really forgot to mention it here. Yeah, well, it's let me just say well, let me just spell it out here so that you're not too confused, actually. Let me even pick a different color. Well, as a category, this is just a take the well, probably should define it here first. Yeah, so when you talk about a smooth family of smooth vector spaces, well, what is it exactly? For every Cartesian space S, I have to specify what it means to give a smooth family of S-index smooth vector spaces. And what's that going to be is going to be precisely a module over what I can call, I guess, C infinity of S with vowels R, but C infinity itself is underlying. So just like R C infinity, which is a sheaf of commutative rings, this infinity will also be smooth. So this underlining is important. It's no longer just modules over the usual ring of smooth functions, but considered together with a smooth structure, which will eliminate the pathologies we previously observed. So now I can define, with this definition of the smooth category of smooth vector spaces in hand, I can define completeness and separatedness as before. And this will be sort of what I need here for I-indexed families. If you have a smooth category, it's very easy to talk about smooth families of objects in a smooth category. So that's what's basically known as the internal Hom. Let's see, how should I phrase this? So evaluated on some S is equal to a C infinity vector Cs evaluated on I times S. So I, recall, is a Cartesian space, and S is also a Cartesian space. So I times S is itself a Cartesian space. So you can now see why sort of smooth categories are the correct setting to talk about smooth families of objects and morphisms, because I was able to, just by having smooth vector spaces as a smooth category, I was able to define I-indexed families of objects and morphisms, again as a smooth category, just by exploiting the structure of a sheaf. And that's what is placed here on this side.
So I guess if I is a smooth set, you use the co-unit lemma and take a co-limit.
Correct. Yeah. So in general, you will be. I mean, yeah. I mean, you really can think of this as the internal Hom. Well, I guess it's not really internal Hom, but what is known as a co-powering, and powering of the smooth category by I, and powering will send co-limiting I to limits of categories. So yes, so you would present it as using the co-unit lemma as a co-limit of representables, and then for each representable, you know what to do. Therefore, you know what to do in general. Yes. Okay, so now we are ready to describe the right adjoint and the left adjoint. The right adjoint is a bit easier. It's what I call the gamma, the smooth global sections functor. gamma simply sends an I-indexed smooth family of smooth vector spaces to the smooth vector space of sections of this family. So formally speaking, I guess, where exactly am I defining this? Maybe I should write it separately. So gamma applied to some family, some object here, let me call it, I guess, V. Well, that's quite literally going to simply be sections, so I-index sections. So this will be a smooth vector space that sends S. Let's hope I don't screw up. Oh, well, it's literally just maps. I mean, morally speaking, this is just, let me just say, this is smooth maps from I to your family V, and by evaluating V as the appropriate object, you can make this rigorous. And the left adjoint functor, that's much more interesting. That's what's called distributions with compact support. And it sends an I-index family of smooth vector spaces to basically what you can call, so V is sent to distributions with compact support on I with values in V. And let me illustrate how the previously discussed unique and co-unique maps now are going to work here. Well, the easier ones will be the unique and co-unique maps for the second injunction, because the second injunction is maybe less mysterious. It's basically some pure categorical abstract nonsense. So the unique map will send a smooth vector space V W, sorry, to a morphism of smooth vector spaces from W to, and now the target of the unique map is going to be take W, take the constant I-indexed family valued in W. So that's just a trivial bundle over capital I with a fiber W, and take its smooth sections. So in other words, you would just take the smooth maps from I to W. And as before, the formalism of smooth vector spaces allows you to make sense out of this. So that's what the unique map is. It simply sends it's like a constant function. Sends a point in W to the corresponding constant function on capital I. What about the co-unit map? The co-unit map of some I-indexed family of smooth vector spaces, say V over I, will be a morphism from the constant family whose fibers are the global sections of the original family, like here. So strictly speaking, I should have indicated like here is a trivial bundle. Yeah, I mean it's going to be slightly messy, but let me say times I projects onto I. And if you look at what happens at a single point of capital I, you will have a map from global sections to V. This will be simply the evaluation map at this point. Okay, so the unique and co-unique maps for this junction are quite easy. The unique and co-unique map for this junction are more interesting. So let me first describe the unique map. So the unique map for some family of smooth, complete separated smooth vector spaces, V over I, will be a morphism of families to the constant family whose fibers are the compactly supported distributions on I with values in V, or more precisely, compactly supported sections of V over I. And what is this map? Well, if we concentrate our attention on the fibers over a single point of capital I, then this map will send an element V of the corresponding fiber to the delta function. I guess I should be more careful. Delta function at the point I of capital I with value V at this point. So that's a delta function, delta distribution of Dirac. We used in quantum mechanics already, and perhaps not for entirely the similar reasons that we needed here. Eventually, we'll see some similar applications of the delta functions here. Finally, what about the co-unit map? As it turns out, if you have a smooth vector space W, the co-unit map will be a morphism from compactly supported distributional sections of the trivial bundle over capital I with a fiber W, or in other words, simply compactly supported distributions on I with values in W. Then the co-unit will send this smooth vector space through W. And that's what is known as the integration map. The integration map for distributions, which as a very special case absorbs the usual integration map for smooth functions. Like for example, or more precisely, densities on a smooth manifold. So if you have a differential form on capital I in the top degree, and an orientation of capital I, together they define what is called a one density, and the one density embeds into compactly supported distributions, and this integral will recover the integral of this one density in the usual sense as it is defined in, say, your favorite textbook on smooth manifolds. So this integrals in particular subsumes integration of differential forms. So you can see already from this fairly abstract setting, which contains hardly any analysis. I mean, the only analysis we mentioned explicitly was the notion of a smooth function. And of course, implicitly hidden here will be the Agamar lemma for smooth functions. But apart from that, there's not much more smooth analysis being used here. So the non-trivial fact is the Agamar lemma. And from this alone, we see how structures like distributions and integration emerge completely canonically in a purely categorical manner. And so perhaps this can convince you to some extent that the formalism we are studying here is not just abstract nonsense for the sake of abstract nonsense, but because actually perhaps capable of handling the actual quantization, not the toy examples you're studying mathematics, but perhaps even something from physics, like quantum mechanics, understood in the usual sense. We should be able to pull it out using this formalism. All right.
So Dmitri,
yeah.
I guess you also developed a general setup for what a smooth limit and a smooth co-limit would mean, and smooth Khan extensions and the like.
Correct. Yeah, you can also talk about smooth Khan extensions. And in fact, smooth Khan extensions are also known as, I claim, quantization. Because quantization will really be defined as a, well, let me just give you a really stupid example. So we are going to define the smooth category of Bordisms equipped with, where Bordisms are equipped with a map to some fixed manifold M. M is known as the target of your field theory. And there is a forgetful map that takes a Bordism with a smooth map to M and forgets the map to M. So this maps because the Bordism category just d-dimensional. So this is a forgetful map. Let's say you have a pre-quantum data which encodes the classical action studied in physics, like for example the Young-Mills action or the Maxwell action for electrodynamics or whatever. So this, and together with the so-called topological sector, which, for example, in the electromagnetism can encode the Dirac charge quantization, which basically tells you the classical electromagnetic field is not really a differential true form encoding the Faraday tensor, but more like a principal U1 bundle with connection. And the pre-quantum field theory will encode the data of this principal U1 bundle with connection on capital M, let's say. It will encode it as a parallel transport functor for this connection. So now you're in the setup where smooth Khan extensions make sense. So we think there should be a left Khan extension and a right Khan extension. And these both should be called quantizations, the left quantization and the right quantization. So what's the difference between left and right? Well, the left quantization will produce, like the usual quantization, you would want to get a Hilbert space, but in physics, they will typically get, at least if you look at what they're doing, more or less, you will get what is called a rigged Hilbert space, which is a dual pair of vector spaces, something like maybe smooth functions or smooth sections of your, say, Springer bundle or whatever, and the distributional sections. And so the point is that the left Khan extension will give you like something like a bra vectors, and the right Khan extension will give you the ket vectors. So smooth functions versus distributions. And that's why you have two of them, left and right, because you want to bra vectors and catch vectors. That's a work in progress, by the way, so we don't have a complete manuscript yet, but in principle, we understand how it should work, yeah.
And so how, maybe
Mhm.
one more question. So
Mhm.
first of all, I guess we could easily replace the infinity set by any smooth infinity groupoid or something like that, right? So
Which one of the C-infinity sets? Sorry. You mean infinity groupoids in the sense of higher gauge transformations, or?
Yes. So instead of like
Yeah.
having smooth limits, we have smooth infinity limits or something like this.
Yes, of course, yeah.
And okay, so and how does this fit in with the ordinary picture of limits and colimits? So in the sense of, does the notion of a smooth limit really give you more, or can we already describe smooth limits by means of ordinary limits and stuff like this?
Well, ultimately, the smooth colimit will unfold into some ordinary limit, but maybe one point to make here is, of course, colimits in the category of complete and separated vector spaces are computed as colimits in smooth vector spaces, followed by the completion and separation functor. And the reason for that is that complete and separated smooth vector spaces form a reflective subcategory of smooth vector spaces. So there's a reflection functor, which is precisely a completion and separation. And that's part of the reason why you see distributions emerging, is because here implicitly there is some completion business going on. But yeah, I mean, ultimately, the left and right extensions will be expressed through ordinary colimits and limits, respectively. But more complicated than the usual ones, of course.
I see. Thanks.
Mm-hmm. Okay, more questions?
Please, may you repeat a bit more about pre-quantum field theories? Reveal a bit more about the idea.
Quantum or pre-quantum? Sorry, say again.
Pre-quantum.
Pre-quantum? Well, this is just encoding the classical action and the topological sector. That's the point. So it's classical action plus topological sector. So for electromagnetism, for example, this would be encoding the action for electromagnetism, which is defined on the moduli stack of all principal U1 bundles with connection over, let's see. Yeah, so the space of fields for electromagnetism would be, say, internal home from M to being U1. And the action functional so what this pre-quantum series actually going to encode is a parallel transport in this bundle. Or if you prefer, the holonomy of this principal U1 bundle, which is exactly the term you see in the action functional. So when you see something like exponent I over H bar like S of something, this whole expression here is precisely the holonomy of this principal U1 bundle with connection with respect to some loop in your manifold capital M. So this arrow, strictly speaking, so this arrow is encoding precisely this term, the exponent of I over H bar of S of something. So that's what this thing is encoding. And that's why I also mentioned that it combines the classical action plus the topological sector, because to define this rigorously, you not only need to know S, but you also need to know the topological sector to add the appropriate topological term here. But that's what this expression, so notice this exponent, by the way, is an element of U1. And that's exactly, so here in this category of values V, for D morphisms, you will typically have U1. So a D-dimensional Bordism will be mapped precisely to this exponential term that you see in the traditional complications for Q of T. So that's what the meaning of the pre-quantum theory is. It's encoding this exponent in a mathematically correct fashion. And now, if you know from the general formalism, you will do some kind of a Feynman path integral of this term here, over all possible spaces of paths, or maybe more generally surfaces or high-dimensional manifolds. And this integral is precisely what is being expressed by this Convex extension. Because Convex extension is like a path integral, really. So these guys are Feynman path integrals. And this is perhaps easier to see in the discrete setting. In the discrete setting, you will see direct sums and products. And you will see they literally take the finite sums of corresponding values, which are the discrete analogs of integrals. So the point maybe here is that we do know that the left and right Convex extension exist for completely abstract categorical reasons. This is basically a variant of the adjoint functor theorem. So, and that's maybe the most exciting part about this, is that we already know the quantization exists. Existence is no longer a problem. So now we know it exists, and we just want to study what we know already exists, which is a radically different approach to the usual, compared to the usual setting where you wouldn't even know how to establish the existence of quantization. So that's maybe the new ingredient that perhaps is interesting.
Thank you.
All right, more questions?
So in GCH, we're always dealing with pre-quantum field theories, right? Or
well, I mean, the way I phrase it here, yes, you will construct a pre-quantum theory using GCH, and then you can try to quantize it using this formalism that I just explained, which exists for abstract categorical reasons.
mm-hmm.
But in principle, GCH also tells you something about the quantized series, because GCH tells you that such a quantized theory will be completely determined by what it does to points here. But remember, points are not quite points. They have more structure. They have a d-dimensional color, which contains a lot of geometric structure. So in principle, the quantized theory has a lot of information. So the moduli gap of points is pretty big. And this also, so applying GCH in the opposite direction sort of gives you maybe one way to sort of study the data contained in a quantized theory. So by passing to the other side of GCH, you can sort of obtain a concise picture of what is inside your quantized theory. Okay, more questions? Okay, I guess in that case, I'll see you guys in 1 week from now, and thanks for listening. Oh, and don't forget, I think Europe is actually switching to the daylight saving time next week, if I'm not mistaken. So I guess next week it will be 1 hour earlier for you guys. If everything is, let's see. Yeah, so when you convert time zones, like let's see, or I guess in the new time it will be 1 hour later, I guess, because we don't. Well, the UTC time is still going to be 3 p.m. 3 p.m. So if you will be on the time zone UTC plus 2, that will be 5 p.m. now, I guess, if I converted everything correctly.
Yes, I think so.
Yeah. At least for the part of Europe that still observes daylight saving time. I know not all countries in Europe do actually. So, like some still practice this stupidity. So unfortunately, that's what we have to deal with. All right, then thanks for listening, and see you guys next week.
Thank you for the lecture. Take care. Bye-bye.
Bye. Bye.